I'm Jinyu from Shanghai Jiao Tong University. I'm glad to introduce our work, which aims to harmonize the tension between performance and isolation in microkernels. This is joint work with my colleagues and my advisors. As we know, a monolithic kernel implements and runs all the kernel subsystems in the kernel mode, which can lead to an extremely large code base. For example, today's Linux contains over 20 million lines of code. During runtime, there is no isolation among those subsystems. A security vulnerability or runtime failure in any Linux subsystem may affect the whole system. On the contrary, microkernels minimize the code running in the kernel mode by moving most OS components such as file systems, the network stack, as well as device drivers into isolated user processes. We name those components as system servers in this talk. Therefore, microkernel-based operating systems can achieve advantages like better security or stronger fault isolation. Besides the success of microkernels in safety-critical scenarios, such as the deployment of QNX in cars, there is a resurgent interest in designing microkernels for more general-purpose applications. Google Zircon is a typical example. However, a cost coming with microkernel is its commonly lower performance compared with its monolithic counterparts. The key factor of such cost is inter-process communication, IPC overhead, between the system servers. Specifically, a system call on monolithic kernel involves only one round trip between the user mode and the kernel mode, and the interaction between different kernel subsystems are finished by function calls. But for a microkernel, different system servers running different user-level processes. Applications need to invoke system servers through IPCs, and the interaction between different servers are also based on IPCs, which makes the whole procedure expensive. We conducted an experiment with SQLite and two system servers, the XV6 file system and a simple RAM disk. The results show that the IPC overhead is considerable in IPC-intensive workloads, specifically when the underlying microkernel is SEL4, which does lots of optimizations for its IPC. Only about 60% of the time spent on the servers are used to do real work. If the underlying microkernel is Zircon, which does not embrace those optimizations, the IPC cost will be even much higher. Actually, IPCs not only bring direct costs such as privilege switch and process switch, but also cause indirect costs, including pollution to the CPU pipeline, cache, and TLB. Motivated by this, our goal is reducing the IPC overhead while maintaining the isolation guarantee in microkernels. Recent hardware brings opportunities. Intel CPU adds a new hardware feature named Protection Key for Userspace, abbreviated as PKU or MPK. This feature allows to create isolated memory domains in a single address space. More detailedly, in each page table entry, there are 4 bits to represent the memory domain ID that's named PKey. So, a single address space can be divided into 16 memory domains, and each memory page belongs to one of them. This feature also adds a per CPU register named PKRU. It marks the rewrite permission on different memory domains. A thread can change its rewrite permission on different domains by directly modifying this register instead of modifying page tables. This feature has been exploited by prior work to achieve efficient intra-process isolation. Prior studies such as Erin and Haibo leverages Intel PKU to build isolated domains in the application processes. Thus, mutually distrusted modules can run in the same process. The efficiency of such design is twofold. First, memory access checking is done by the CPU without leading to any software overhead. Second, switching between different modules are achieved by simply modifying the PKIU register, which only takes about 28 cycles. The system servers on microkernels are mutually isolated and they have well-defined interfaces, which just matches the idea of intra-process isolation. Therefore, in this work, we want to introduce intra-process isolation to microkernels to achieve our design goals. The first design choice is organizing different system servers into the same user-level process. The isolation between different servers is guaranteed by the PKU-based intra-process isolation mechanism, so the communication cost between different servers decreases. But an application still requires to invoke a server with traditional IPCs. If the invocation only requires one system server, such a design cannot benefit the performance. The second design choice is to run the system servers within an application's address space. Therefore, the performance problem in the first design choice is avoided. However, this design has several major drawbacks. First, it requires to map a server into multiple applications' page tables, which makes updating the server's memory mappings especially expensive, since it needs to update all the application's page tables. Second, the cost to setting up the IPC connection is non-negligible, because mapping a system server requires intensive page table modifications. Third, this design restricts the application's ability to use the whole address space as well as the PKU hardware. Therefore, both of our initial designs are not satisfying. Fortunately, we have a new observation on the PKU hardware. As its name indicates, PKU appears to only take effective in user space. However, we observe that no matter in kernel space ring 0 or user space ring 3, PKU-capable CPUs transparently enforce permission checks on memory accesses only if the user kernel bit of the corresponding page table entry is user, which means user accessible. Hence, PKU as a lightweight hardware feature also offers an opportunity to achieve efficient intra-kernel isolation if all the page table entries for the kernel memory are marked with U bit instead of K bit. Based on this observation, we propose the final design named UnderBridge, which leverages the PKU hardware feature to achieve intra-kernel isolation and syncs the system servers into the kernel space while maintaining their well-defined IPC interfaces. Generally speaking, UnderBridge puts the system servers, which are user-level processes in traditional microkernels, back into the kernel space. Like a monolithic kernel, it only takes one round trip between user and kernel for an application to invoke a system functionality. Also, the interaction between different system servers becomes more efficient since no address space switching is required. UnderBridge constructs execution domains with PKU in the kernel space and let one system server execute in one execution domain. Different execution domains can be connected by IPC gates. One thing to mention, to use PKU in kernel space, UnderBridge tags all the kernel memory pages as user accessible in the kernel page table, as said before. However, marking kernel memory as user accessible enables unprivileged user space applications to access kernel memory directly. So UnderBridge maps the kernel, makes the kernel to use a separate page table. UnderBridge builds isolated execution domains over PKU memory domains and confines each system servers in an individual execution domain. Execution domain is specialized for running the trustworthy microkernel. Every other execution domain has a private memory domain and can only access its private domain by default. A system server exclusively running in one execution domain stores its data, stack, and heap regions in its private memory domain, which cannot be accessed by other servers. UnderBridge ensures an execution domain can only access allowed memory domains by configuring its PKIO register. It also forbids the execution domain from modifying this register. Shared memory between two servers is allocated by allowing them to access a free memory domain together. Shared memory between a server and a microkernel does not occupy extra free memory domain because the microkernel can directly access all the memory. Even though the system servers reside in the same kernel space, they are isolated from each other and their IPC interfaces are preserved. When connecting two system servers in the execution domains, the microkernel generates an IPC gate for them. The IPC gate resides in memory domain 0, which can only be read or written by the microkernel. So, for servers, IPC gates are execute only. During an IPC invocation, the gate transfers the control flow from the caller to the callee. To be more specific, it saves the caller's execution state, switches the callee's execution domain by setting the PKIO register, and restores the callee's execution state. Besides, IPC gates also exist between the microkernel and the servers, which enables the interaction between the microkernel and the servers. Those in-kernel system servers invoke system calls through dedicated IPC gates connected with the microkernel instead of using syscall instructions. SPKU provides 16 memory domains in total, and each execution domain requires to exclusively use one memory domain. UnderBridge can support at most 16 execution domains concurrently, including the reserved one for the microkernel. Nevertheless, more system servers can be required considering the number of different device drivers. When the number of concurrent system servers exceeds 15, one solution is time multiplexing, but it will not only restrict the concurrency but also incur non-negligible switching overhead. Therefore, UnderBridge enables server migration, which can dynamically move servers between user and kernel space. To ease the migration procedure, the microkernel aligns disjoint virtual memory regions for different system servers. Whenever runs in an execution domain or in a user process, a server always uses the same virtual addresses. According to either online or offline profiling, UnderBridge can run frequently used or performance-critical servers in kernel space, while accommodating other servers in the user processes. In traditional microkernels, system servers only have ring 3 privilege. To achieve the same security and isolation guarantee as the traditional microkernels, UnderBridge should restrict the server's behavior when running them in ring 0. Otherwise, a compromised server may fund and execute privileged instructions at unaligned instruction boundaries with ROP to threaten the whole system. One possible defense solution is to enforce control flow integrity, which ensures the servers cannot execute any illegal control flow leading to executing privileged instructions. However, CFI instrumentations inevitably brings obvious runtime overhead. Another common solution for the similar problem is binary scanning and rewriting, which ensures the unwanted instructions do not exist in the code. However, there are too many privileged instructions which make such solution infeasible. For example, the halt instruction only takes 1 byte. It is almost impossible to eliminate such instructions. So, UnderBridge combines the usage of hardware virtualization and binary writing to prevent the execution of privileged instructions in system servers. UnderBridge runs the microkernel in the non-root mode and deploys a tiny secure monitor in the root mode. For most privileged instructions that are not in the critical passes, such as halt instructions, we configure them to trigger VM exit and enforce permission checks in the monitor. For others that exist on the critical path, such as writing CR3 instructions, we carefully handle them using binary scanning and rewriting. Such a hybrid solution is both efficient and effective. Due to the time limitation, this presentation skips some parts like how to authenticate IPC capability. If you are interested, please refer to our paper. Let's have a quick look on the performance gain brought by UnderBridge. We measure the round-trip latency of invoking an empty function in one server from another server. This figure shows the absolute cost of cross-server IPCs in different designs. The latency of an IPC round-trip in UnderBridge is around 109 cycles, which is dominated by 2 PKU writing instructions. Compared with SkyBridge, which is the state-of-the-art optimization for IPC in microkernels by using VMFunk, UnderBridge is still faster because SkyBridge requires too much higher VMFunk instructions. To demonstrate UnderBridge's efficiency, we also ported it to 3 popular microkernels. We evaluate the throughput of SQLite application with YCSB as a workload, which represents an IPC-intensive benchmarks. For SEL4, which is the most efficient one among the 3 microkernels, UnderBridge can improve the application throughput by up to 105%. Compared with SkyBridge, UnderBridge can also improve the throughput by up to 35%. So, in IPC-intensive benchmarks, UnderBridge can bring obvious performance benefits. In one word, UnderBridge leverages PKU-based intra-kernel isolation to redesign the runtime structure of microkernel OSes for faster system services. Besides, such an efficient intra-kernel isolation mechanism may also be used to harden the isolation of monolithic kernels. That's all. Thank you for your listening.